Welcome everyone. For today's prep, we're going to start looking at antidifferentiation. So we will be starting with the definition here, so what an antiderivative is. But before we get to this, I just want to look at the big picture. So what are we actually going to be doing here? So let's suppose we start with a function. We'll call it capital F of x. And everything we've done in the course up to this point has involved finding the derivative of a function. So we've learned a whole bunch of derivative rules that allow us to take one function and produce its derivative. So we've learned the differentiation process. How to take one function and differentiate it. What we're going to be doing now is rather than starting here and trying to produce its derivative, we're going to be looking at, can we take that derivative and go backwards? Can we, if we have the derivative, can we recover that original function? And as we're going to see, the answer is yes. And we call this process finding the antiderivative or antidifferentiation. So this function here is called the antiderivative. This over here is called the derivative. All right, so what is the definition for an antiderivative? So we say that function capital F is an antiderivative of some other function little f if when we differentiate capital F, we get that function little f. So this is our antiderivative, and if we differentiate it, we get capital F prime, and this is equal to the other function we're interested in, little f of x. So let's get a little practice working with this definition. So let's consider the function little f of x equal to x squared, and we're going to show that each of these functions is an antiderivative of x squared. So let's start with this first one, the 1/3 x cubed. Let's start with that one. And we'll do our work over here. So how do we show that this is an antiderivative? Well, we're going to take the function and we're going to differentiate it. So right now we're right here. We're taking our function and we're going to try calculating our derivative. So we've learned a whole bunch of derivative rules. So the 1/3 that's in front just kind of stays there in front. We don't do anything with it. And then we focus in on our variable part and we get to do our derivative power rule. So we bring down the 3, we keep x the same and subtract 1, and then the 3 and the 1/3 cancel, and we're left with just our x squared. And that's what we wanted. So what we just showed is that when we take this function and we do its derivative, we get x squared. All right, so that shows that the function 1/3 x cubed is an antiderivative of x squared. It's the stuff that comes before we do the derivative. All right, well, what about this other one, 1/3 x cubed plus 1? This is a completely different function than that 1/3 x cubed, but we're going to see that it actually gives us the same thing, because when we take this 1/3 x cubed, we know what happens when we differentiate that. So the 1/3 x cubed here, when we differentiate that, is going to give us the x squared. And then what happens to this plus 1? Well, when we have a constant all by itself, the derivative of that is just 0. So we would end up with x squared plus 0, which is just x squared. So the main action here is happening with this variable part. Same thing if we have the function 1/3 x cubed plus 2.5. Well, we've got that main variable part, and then we're adding on a constant. So when we do the derivative of this, same deal. The variable part here differentiates to the x squared, and then the derivative of that constant that's all by itself is just plus 0. And then same thing in the last one, the 1/3 x cubed plus 5, well, differentiate, and again, the variable part is still differentiating to the x squared, but the plus 5 is just a constant, so that differentiates to just 0. So every single one of these functions over here is an antiderivative of x squared. So these are what come before we do the derivative. All right, so what we're going to see is in a few seconds, we're going to see how do we start here and how do we get this function? How do we figure out the 1/3 x cubed? Or if we're starting with x squared, how do we go back and figure out the 1/3 x cubed? Now, one thing before we get there, though, what this example shows is that adding on a constant doesn't really change the fact that we have an antiderivative. So the main focus is going to be on getting that variable part, and then we can add on any constant that we want, and it'll still be an antiderivative. And the reason why we can do this is because of this rule that says all of the different antiderivatives, well, they just differ by a constant. And the way we're going to indicate this is we're just going to put plus c at the end of our antiderivative. So we're going to put plus c at the end of our antiderivative, because it doesn't really matter which constant we add on at the end, we're still going to have an antiderivative. So we just kind of leave it arbitrary. So a lot of times we'll call this an arbitrary constant. So we just kind of leave it vague. All right, so the notation we're going to be using for finding antiderivatives is, we call this, it's going to be integral notation, and we're going to be looking at what we call the indefinite integral. So in the notation here, we're going to have an integral sign and a dx at the end, kind of like the dx when we do derivatives, dx. So this is, we call this our integral sign, and it means find the antiderivative. The differential here tells us the variable. So what this is telling us is find the antiderivative of the function little f of x with respect to variable x. So the x here in the differential is telling us what the variable is. And this is the function we're trying to get the antiderivative of. So we call this the integrand. It's the function we're trying to integrate. So we get the main variable part then of our antiderivative, and we throw our plus c constant on at the end. All right, so let's look at a few basic antiderivative rules. So the first one says, what happens when we differentiate just a constant? So here we're integrating just a constant k. Well, what do? So we're integrating this constant function with respect to x. So we want to find the antiderivative of k with respect to x. So what this rule says is we take the constant k and we multiply it by our variable. So our variable is x, so we're going to multiply it by an x. And then we throw our usual plus c on at the end. Now, why does this work? Well, the nice thing with antiderivatives is once we think we have the answer, we can always check our work. So we can check this out. So let's do that. So what we're doing here is we're taking our constant and we're finding the antiderivative. So let's take what we think the antiderivative is and let's differentiate it, and we should get back to where we started. So let's try it out. So if we differentiate k times x, well, the k is a constant multiple, so it sticks around. The derivative of just the x is 1, So we end up with k times 1, and then the derivative of a constant all by itself is 0. So our derivative here is k. So what this rule is telling us is how to go back. So if we have k, a constant all by itself, we're going to do the integration process to recover the antiderivative, what came before. Now we also have an exponential rule. So how do we differentiate when we have a function e to the kx, where again k is just a constant? And how this one works is the exponential part stays exactly the same, so it's just going to stay e to the kx. But then we take that constant k and we flip it and put it in front. So we end up with a 1 over k in front. Now a special case of this is, what is the antiderivative of the function e to the x? Well, we know e to the x is a special function. It's its own derivative. So it also is its own antiderivative. And then we put our plus c on at the end. So this is the special case if that constant k is just 1. So we just have x. All right, so the one main rule, probably the one we're going to be using the most, though, out of these, is this power rule. So this is the integration version or anti-differentiation version of power, the rule for power functions. So it tells us what to do if we have a power function x raised to some power n. And what we do is we keep x the same, we add 1 to the exponent, and then we take the new exponent and we put the reciprocal in front. So when we do this, you want to think of this fraction that we're putting in front. This is the reciprocal of the new exponent. So when we do the power rule, you want to do this one kind of last. You want to do this when you do this, you want to leave some space in front of your x. So you do this one last. So the first thing you would do is you would first keep whatever variable you have the same. So if you're dealing with an x, your antiderivative is going to be an x. If it's t, then your antiderivative is going to have t. So first thing, keep variable the same. Then, once you have that, the next step is to add 1 to our exponent. I guess green. So step 2, add 1 to get the new exponent. And once you have that new exponent, so how this would work, how this is going to look, we're going to first write down x. We're going to leave a space here. Then we're going to add 1 to the exponent. And then once we see what that new exponent is, we're going to put the reciprocal in front. Now this power rule works for all n except -1. So if this is x raised to the -1, this rule doesn't work. And instead, we end up with the other one here. So this is telling us what happens when n is equal to -1. So this is kind of like the one special case of our power rule. And what happens is when we're dealing with x to the -1, or just 1 over x, we end up with the natural log function as our antiderivative. So ln absolute value x. All right. So let's try a few examples of these rules. So let's look at the first one here. We want to find the antiderivative of the square root x function with respect to variable x. Now, just like if we were trying to do the derivative of this, we're going to rewrite root functions. So if we have the nth root, we want to rewrite that as a raised to the 1 over n power function. So before we find the antiderivative, that's exactly what we're going to do. We're just going to rewrite that function. So we're going to rewrite it as x raised to the 1/2. So once we get that, now we're ready to do our power rule. So again, when we're all set to do our power rule, leave a little bit of a space here because we're going to be putting some stuff. Our variable is x, so we're going to keep it x. And then we're going to add 1 to our old exponent. So 1 plus 1/2 is 3/2. And then we take this new exponent and we flip it. We put the reciprocal in front. So this will be a 2/3 in front. And then plus c at the end. So again, for this exponent, what we did, and as you're getting the hang of this, it doesn't hurt if you want to do this off to the side. What we really did here is we took our old exponent, which was the 1/2, and we're adding 1 to it. So if we get a common denominator, this is the same thing as 1/2 plus 2/2, and then we add the numerators and get the 3/2. So what we're seeing here is when we integrate power functions, the exponent is getting bigger. All right, let's try the next one, e raised to the negative 2x. So this is our special exponential one. So we identify the k value. So the k value in this case is -2. So that's the constant in front of the x there up in the exponent. And when we do our antiderivative rule, the exponential part stays exactly the same. So it'll be e to the negative 2x. But then we take that constant k and just flip it. Put the reciprocal in front. So we end up with -1/2 in front, and then our plus c at the end. All right, and that's our antiderivative. So we're seeing essentially how this process reverses. How can we undo the derivative? That's what we're seeing here. So we're the term inside here, this is actually the derivative, and we're undoing that derivative process to see what came before. All right, so let's try the last one here, 1/x². And if we wanted to differentiate this, what would we do? Well, we would write this as a negative exponent. So we're going to use that same strategy. We're going to rewrite fractions with negative exponents. So a lot of our strategies are going to be similar to what we did with derivatives. So we'll write this as x raised to the -2. So we just make the exponent negative. We get rid of the fraction. And now this is a power function. So now we're ready for our power rule. So we keep x the same. Again, leave a little bit of a space here. Probably left too much of a space there, but what are you going to do? And then we add 1 to our exponent. So we're going to take us up to, so we're at -2. And again, it doesn't hurt. If you want to do this off to the side, as we're getting the hang of this, we're taking our old exponent, which is -2, and then we're adding 1. So that gives us the new exponent of -1. Okay, so once we know what our new exponent is, we put the reciprocal in front. So we're going to flip it. So we end up with 1/-1, and then our plus c at the end. Perfectly fine to just leave it like this, but 1/-1 is just -1. And a lot of times with negative exponents, it's helpful to write them back as a fraction. So if we wanted to, we could rewrite this antiderivative as -1/x plus c. But again, perfectly fine to just stop there. All right, so we're going to be practicing some more of these in class, and we're going to start looking at some properties that allow us to take individual pieces like this and combine them together. And we'll see how the differentiation process works if we have addition or subtraction, or multiplication by a constant. So we'll see you then. Bye-bye.